Hello and welcome to the Spring 2020 Great Questions Lecture. We are meeting in a format that's different from our usual lecture hall, online today via Zoom with Krishnan Venkatesh of St. John's College in Santa Fe, New Mexico. Of course, we're meeting this spring because in-person meetings are impossible due to the coronavirus pandemic. Today's conversation is going to focus on Euclidean geometry. Our discussant today, Krishnan Venkatesh, studied English literature at Magdalene College, Cambridge, and worked on Shakespeare at the University of Münster, Germany. He taught English literature and philosophy in China for 3 years before discovering St. John's College in Santa Fe, where he has taught for 30 years in both Western and Eastern programs. I'm delighted to invite Krishnan to speak with us this morning. I'm coming to you from Austin, Texas, and Krishnan is over here in Santa Fe, New Mexico. And Krishnan, it's wonderful to welcome you this morning. I am also, I am a graduate of St. John's College, Annapolis, Maryland, which is where I initially fell in love with Euclidean geometry. Before we start talking about Euclidean geometry, the topic of today's talk, of course, is Euclidean geometry, food for the soul. I'd like to ask you just a little bit about liberal education. What in your opinion, is the value of liberal education? What is it good for, and why should students pursue it?
That's an excellent and huge question, Ted. Obviously, I've been thinking about this for 30 years. So, I mean, just to give a brief reply to this, I think that one of the things we learn in the seven liberal arts, the traditional 7 liberal arts, which is mostly mathematical. It's so there's grammar, logic, rhetoric, the first one. So the first 3 called the trivium. Then you have the quadrivium, which would include music, astronomy, arithmetic, and geometry. And those were the traditional 7 liberal arts that modern liberal arts education is based on, that liberal education is based on. And they were liberal because they were freeing. The word liberal comes from same root as liberate. And so they were freeing. What did they free? So they free the mind to see the truth. Part of what each of those 7 liberal arts traditionally does is that it goes to the underlying structure, the foundational principles of these various disciplines. So if you're looking at astronomy, for example, you're going to look at the fundamental structure of astronomical thinking and master those, which then enables you to think for your own further and to make discoveries for yourself. Same with grammar, for example. If you study Latin and you study Latin grammar, then what you have is a kind of understanding of the fundamental structure of a language, what has to be there in a language, which makes it easier for you to learn other languages. So it's freeing in that way, is that it creates a kind of independence, a kind of confidence and autonomy in that. So the traditional liberal arts were like that. In the modern world, we've added liberal arts like history and English and comparative literature. And those obviously are not so much about going to, finding some certain abstract fundamental principles, but those arts end up making things complex. So, so I'd say that in studying history, you're studying human types, you're studying types of interactions, you're studying types of causation, types of consequence, and learning how to think causally, but in a complex world, in a complex, messy world. So you're getting something of that liberal arts understanding of the fundamental principles of how things work, but you're also learning through books like Herodotus, Thucydides, you're also learning to grasp how these principles play out in a messy world. So I think that on both fronts, kind of like in a way, like simplifying, going to the simple abstract principles that underlie all things, like in mathematics, on the one hand, and on the other hand, complexifying, history and literature, going for the trying to see how certain principles interact with a world that is much messier than the world of mathematics. So modern liberal arts, I think, does both, or should do both.
All right. Let's discuss now a core component of liberal arts, at least as studied at St. John's, and of course in our Great Questions seminar, where students in our first year seminar study book 1 of Euclid's geometry, and it's an exciting study. The way we do it at Austin Community College is we weave the discussion of Euclidean geometry with the discussion of global religious texts and global poetry. How did you come to discover Greek geometry, Krishnan?
A long and winding road. When in my previous life, before I came to St. John's, which feels like about 10,000 years ago, I was an English literature scholar, and my field was late medieval and Renaissance literature. And in that period, I noticed that every single great writer was immersed in astronomy. If you've read Dante, you know how closely he tracks astronomical changes. So when he points to the position of planets in the sky in relation to certain stars, he's not only giving you time and place, very, very exactly, but also but also these things have a kind of theological significance in Dante. Same with Spencer, and my beloved Chaucer, for example, my favorite English poet. Chaucer wrote a treatise on the Astrolabe, which is an instrument for measuring the movement of the stars, the position of the stars. And this treatise on the Astrolabe is about 100 pages long, and Chaucer wrote it for his son. And it's the first treatise on an astronomical, on a scientific instrument in English. And so obviously this stuff was very important for the early, for poets, of all people, poets. Mm-hmm. And looking at Chaucer's treatise on the Astrolabe, it's not only that they knew how to consult the star charts, but they actually knew how to work with the phenomena of the stars and the planets, but also could do the math and could do the calculations. So I thought, these people have a different relationship to the world than I do. My position as a modern man, I hardly ever look up, right? I think most of us don't look up. It's been said that one of the strange phenomena of modern times is the modern ceiling. The modern ceiling is blank, right? You think about the ceiling of medieval churches or medieval buildings, Renaissance buildings, they're painted. Montaigne's library had inscriptions, had things carved in it, in the ceiling. Yeah, but our ceilings are blank. Why? Because we never look up. Our perspective is all horizontal. So then I thought, these guys that I love, these early poets, they're always looking up. Clearly they had no street lights, so the stars were more evident to them. But they were also attentive to the sun, and they could do the math. So when they did the math, they had access. They knew how to connect both the physical phenomena of what they saw, and also something abstract that enabled them to make predictions about things. And I thought, that's a very different way of relating to the universe. These people have a physical orientation to something unchanging. And so I want to know what they had. And so then I started thinking, what did they study? And they all studied Ptolemy, right? So around 100 AD, Ptolemy was a mathematician who wrote in Alexandria, what is now Cairo, and Alexandria was one of the hubs of Western civilization. And so Ptolemy did a huge astronomical work called the Almagest that predicted the movement of the planets, predicted the position of the planets as well as the sun. And so I thought, all my beloved authors, they knew their Ptolemy backwards. They were intimate with Ptolemy's thinking. And so I thought, I have to read Ptolemy. And so I went and I got a volume of Ptolemy, and I couldn't understand a thing. And it's partly because he draws heavily from Euclid. All his math comes from Euclid. And not all, 90% of his math comes from Euclid and subsequent mathematicians whose thinking is formed by Euclid. So I start to try to read Ptolemy, and I can't understand him. And I thought, who around me can help me to understand this? And of course, in an English department, nobody studied Ptolemy. And if I go to mathematics, no mathematician or physicist that I knew was interested in this ancient geocentric view of things. To them, why are you interested in this? So I was helpless. And many years later, I discover, hey, there's this college in America, this very strange college in Annapolis and Santa Fe, where not only do they study Ptolemy, they spend 2 or 3 months studying Ptolemy, but they also spend almost 8 months studying Euclid, which is the foundation of Ptolemy. And I thought, so I popped that in my mind, thought, oh, that's very interesting. Maybe I need to go someplace like that. So it was through poetry, through the great Renaissance poets, and then through Ptolemy, that I then ended up becoming very interested in Euclid. And this was one of the impulses for me to seek out St. John's.
It's very interesting, especially the reflection about the modern ceiling. I wonder, having now, and this may be a better question for the end, but it's I'll ask it now. After that's my rooster.
Wake up!
he thinks we're always asleep. Having now, spent a long time focused on Euclidean mathematics and ancient astronomy, going back to Renaissance literature and poetry, do you have a different perspective on it now, having studied mathematics and classical astronomy?
Oh yes. So I'm more in tune with what these poets are doing. For example, with Chaucer, I now understand what he's saying, for one thing, and then I can also tell when he's making a joke, when he's saying something that is just astronomically not right, and and with Dante also, all three books of the Divine Comedy, they end with the word stars, and so they're about like looking up at the stars. And so there's something about when you spend a lot of time looking at the stars and looking at the sun, it really kind of puts you more in where Dante is. It's very, it's almost physical.
Yeah.
So you get a kind of intimacy.
Yeah. And I imagine it also, changes the way that you look at the night sky as well, and perhaps provides more of an impetus to look at the night sky.
Yes, for sure.
Yeah.
For sure. It's a mind blower for most students here when we have them look at the night sky, and many of them who live in big cities, they have no idea that the heavens appear to revolve.
Yeah.
And so when they see that, it changes your life. And in New Mexico, this is the first place that I've lived where I realized that every star actually has a different color. I didn't know that before. I just thought they were white.
Well, apart from the having a deeper appreciation for poetry and literature through the study of classical mathematics and astronomy, studying Euclid is sort of intrinsically interesting and enjoyable for its own sake. So what's so great about Euclid's elements? Okay,
so for those of you who are watching who have not encountered Euclid's elements, let me first introduce you to Euclid. So so this is Euclid's elements, and those of you who've been using the Green Cat edition, you'll recognize the format of this. This is the Green Lion edition of the whole thing. It's pretty thick, right? And it contains 13 books of mathematical proofs. Now, this is what's very interesting to me about this. Let me see, I'm going to find the pages here. The whole edifice starts from 2 pages of axioms. 2 pages of axioms. Now, what are axioms? Axioms are definitions, definitions of the geometrical entities that they're going to use. You know, so an example of a definition is a point. What's a point? You need a point in to do geometry. So a point is that which has no part. Right? And I'll talk about that a little bit later. What's a line? A line is breadthless length. A line is breadthless length. And so those are examples of his definitions. And then he has a bunch of definitions, and then he has a bunch of postulates. And postulates are, the Greek word that postulates translates means something like something begged, something asked. You know, so for example, to draw a straight line from one point to any point, that's a postulate. So I ask you that you grant me that I can draw a straight line from one point to any point, right? And I ask you to grant me that I can extend it indefinitely. So the postulates involve the actions that make geometry possible. And then you have a third kind of axiom called common notions. And common notions, they're common because they're common to all fields of thinking. And an example of a common notion is things which are equal to the same thing are equal to one another. Right? That's an example of a common notion. You know, so if A is equal to B, and if C is equal to B, then A is equal to C. Right? So these are like fundamental notions in human thinking. You can't really think without these. And so these are 2 pages of axioms. And from these 2 pages of axioms, he gets this whole thing. And so where does it go? So in book 1, we're dealing with triangles. You know, so book 1, 2, and 3, we're going from triangles, parallel lines, and we're going to complex polygons. And then in book 5, this very weird and interesting thing happens. Book 5 is like the most important bit of Euclid and the most beautiful book in Euclid. And book 5 deals with proportions, right, which in Greek is analogia, analogy. And it's an extraordinary work because the idea of proportion underlies the whole of Greek thinking. And it's what makes Greek thinking distinctive. Anyway, so for proportion, you then apply it back to geometry and see what you can do once you have proportion. And then after that, you get a bunch of books about numbers. You know, so it's not just geometry. He has like proofs about so prime numbers, perfect numbers, lots of different ways to think about numbers. And some of the fundamental proofs of arithmetic is in this book. And then you get to irrational numbers. You know, so you have about a 90-page book 10 on irrational numbers, and that's really exciting. You know, and then right at the end of the book, we're dealing with solid figures, 3D, and complex solid figures like regular solids, like dodecahedrons, icosahedrons, and you're learning how to inscribe them in spheres, and circumscribing around spheres. You know, so putting these 3D solids in spheres, around spheres, and so on. So it gets pretty complex. And so the book 1 is the beginning. Book 1 is the foundations. But where it goes is just astounding. And it's astounding that you can go there with these 2 pages of axioms. Now, when you then get to the astronomy, so we're thinking astronomy from Ptolemy to Newton, pretty much. They're working with the same geometry, with Euclidean geometry. And in Ptolemy, let's say, you have a kind of diagram that's very interesting, where you get a kind of bird's eye view of the solar system, with the sun in the center and the planets going, with the earth in the center, right? And the sun and other planets going around the earth. And so you get this bird's eye view that is not a view that any human being could have, certainly at those times, this bird's eye view. And then the geometry is made using circles, using spheres, so all of Euclid is plugged in to the astronomical phenomena, such that you can now make predictions. You can use Euclid to model the movement of the stars and the planets to make predictions. And the predictions are amazingly accurate. You know, geocentric astronomy could make very accurate predictions. You could predict, after 2 months of studying Ptolemy, if I asked you, can you find out where exactly in the sky the sun was at 2 p.m. on February the 26th, 728 BCE? After about an hour, you could tell me where it was, and it would be pretty accurate. So this whole edifice of early science, as it were, you know, so early astronomical thinking, but also mechanics. I'm thinking Archimedes, you know, mechanics draws from Euclidean mathematics, and it's a gigantic success story. You know, so when you think about it, these axioms, 2 pages of axioms and the powers of the mind, actually enable you to find out new things, not only about math, but also about the world. So you find and this goes on for 2,000 years. You're using this math to find out new things. And I think that this success story is very important for anybody who's working in liberal education, because it may be the greatest success story of the West, because what it shows is the power of reason, right? You know, so from these 2 pages of axioms, you can reason your way to understanding very important things about the universe that you live in, and even discover figures that you don't find physically. And this to me, as the more I think about it, it's amazing. You don't find this in Eastern thought, right? You know, so this phenomenon of, we call it axiomatic geometry or axiomatic mathematics, where you have a mathematical edifice that is drawn from a small body of axioms. And it doesn't exist in India. It doesn't exist in China. All right, so they had mathematics and they had brilliant mathematicians, but they didn't have axiomatic mathematics, which give you I don't know, an edifice, a building that you can construct more on for I said, for 2,000 years. And this is very powerful, because when you think, okay, imagine yourself to be living in a culture where there wasn't any axiomatic mathematics. What would you think thinking is? What would you think about the power of reason? Now, in the West, because we have this, we have great faith in the power of reason. We think we can go a long way with reason. You know, we see it, and the other side of it is the idea of the demonstration. That axiomatic mathematics, it's built on the idea of a demonstration, that you can give an enunciation, and then you can demonstrate the enunciation, drawing from the axioms and previous proofs. Now, if you didn't have that as a model for thinking, then what would it feel like? Right? So you say, those of you who are studying Chinese poetry, what would it feel like if you were the kind of person who didn't have any experience of, say, geometry, or any example of the power of reason? Anyway, so this is why I think it's so what Euclid does is so radical and fundamental, that in a way that we miss out if we miss out in liberal education if we never encounter Greek geometry.
And this is an area that I just really don't know much about at all. But what about astronomy in the East? What did astronomy? I mean, clearly we looked at the same sky, but you're suggesting we had different experiences of it. Are you suggesting we had different experiences of it?
Yeah. Because what someone like Ptolemy does is that he takes the phenomena of the heavens, and he notices irregularities in them. You know, so then in the phenomena of the heavens, the things are not perfectly regular. Like, it takes the sun longer to go around 180 degrees, the first 180 degrees, than it does to go around the second 180 degrees. Why, so why? So then what Ptolemy does is, taking Euclid, he works at it until he discovers some kind of principle of regularity, where the anomaly, the irregularity, can be taken into account of. But this is because he's going kind of deeper than the phenomena to find a mathematical principle where you can make a model, right? So you can make a model, then you can work out where it's supposed to be at any given time. And this idea of making a model where you can, and then this is kind of an imaginary model, not a physical one. But if you make a model, you can make very accurate predictions, but you also have some principle of understanding how it might work, right? Why these phenomena might come about in this way. Whereas I'm thinking, I don't know that much about Chinese astronomy, but for say Babylonian astronomy, you could make predictions by making tables, or imagine drawing graphs. If you draw a graph, you could probably have a pretty good idea of where the sun's going to be next, right? And but this is not about understanding a principle, right? So Greek philosophy is about theoria, and you guys probably know that the word theoria, is cognate with theao, which means to behold, to see, right? And theao is also the root of the word theater. So when someone like Ptolemy, when a Greek does mathematics, they want to get a model where you can see the whole at once, the whole principle at once. Whereas, so that's why this driving for some underlying principle is so important in Greek thought, is so that you can theorize, you can behold.
Now, in the East, isn't the searching for an underlying principle not through the realm of mathematics, but perhaps through the realm of story, through poetry, through understanding the world with reference to a story that helps you understand your place in the universe and the reason for the universe being the way that it is, that helps you make predictions of a certain kind, that different from axiomatic. I'm just wondering what the because our axioms in mathematics, where do they come from? I mean, are they strictly speaking rational? So where we go from there, that's the work of human reason, right? Mm-hmm. But then establishing those axioms, is there a relationship between establishing the axioms of an axiomatic system and a poetic interpretation of the whole?
I mean, that's a very big question that you ask, and I'm going to step back a little bit and take a different tack here. Okay. So in Aristotle's Categories, which is the first book of what he calls his organon, which is his body of work that deals with thinking, right? And so say logic is logic, but it deals with the foundations of thinking. The first thing that Aristotle says in the Categories, which is the very beginning of the study of logic in the West, the first thing in the study of logic, he says that there are two ways of speaking, and the one way of speaking is univocal, and the other is equivocal. And so when you use a word like, so univocal means a word has one meaning, right? So you tie a word to one meaning. Equivocal is when a word has more than one meaning, right? So he makes that differentiation right off the bat, that this is important. Now this difference between univocal language and equivocal language is one that we are children of in the West. So let me explain what I mean. So when you're doing law, you expect law to be univocal. There's no ambiguity. Right? When you're doing math or doing science, there's no ambiguity. When you're doing when you're reading a textbook language is meant to be univocal. There's no ambiguity, and all of these presuppose this strange thing called a definition, right? You say, well, what are you talking about when you say this? Well, this is what I mean. And then you give a definition. And now it's univocal. Now you know that you and the other person are understanding the same thing by this. Now, so then Western philosophy starts with this, and starts with, Plato tries to be univocal. So you talk about the virtue. Most of you have read the Meno. So you talk about the virtue, I call it excellence as a translation of the Greek arete. Talk about the excellence of a knife versus the excellence of a man, right? And Socrates would say, well, there has to be something that you mean by excellence that covers the two ways of using it. So Socrates is looking for something univocal in this. There's one meaning to excellence. And whereas it's possible for someone to say that, no, we get bogged down in those virtue words like excellence, because they're in fact equivocal. That what you mean by the virtue of a knife is different from what you mean by the virtue of a man, right? So this differentiation of univocal and equivocal is at the very heart of Western thinking, I think. Math starts with the axioms. Math is the prime example of something univocal. It's the model of reason that works through univocal thinking, and it's the standard, right? The standard of clarity, the standard of precision. But what's it like if you live in a culture where you don't have that distinction, right? So Chinese philosophy, for example, which I love, right, is all equivocal. So when Confucius is asked, like, what's benevolence? He'll say, benevolence is when.
Yeah.
Right? Or benevolence is what you get when this or this happens. So clearly, if you don't make that distinction, it's hard to see how you can have something like axiomatic mathematics or science that comes from axiomatic mathematics. Right? You're going to have brilliant, inspired thinkers that have stabs of insight and penetration, right? But you're not going to have the formal language to make it into a bigger whole. So I do think that the stories, I do think that the even the arguments, the argumentation of Hindu philosophy or Buddhist philosophy, that they're also like full of interesting ambiguities.
That's fascinating. Yeah. And you tie that to, I mean, you really find that the reason for that difference in the two sort of philosophical literary traditions of the East and the West is the presence of axiomatic mathematical thinking in the West and its absence in the East.
Yeah, I think so, and I think that's why, one of the reasons why, in a way, the central example in the Meno is a mathematical demonstration. Right? So you start with something where you can get somewhere by reason. Yeah. Now
the world today is sort of challenging to separate between East and West along these sorts of lines. I read in your biography that you taught in the East for many years. Yes. Yeah.
Yes.
Do you notice a difference between studying axiomatic geometry with? I mean, well, I know so little about this. So I feel very fortunate to have this opportunity to speak with you about this, because I'd like to know more. Studying axiomatic geometry with students in the East versus studying axiomatic geometry with students in the West. Is there any difference, or are things now so completely inundated with axiomatic mathematics, not geometry specifically, but mathematics in particular, that there is no longer that sort of distinction between the East and West along this fundamental line?
Yeah, I think that's right, and I think it's probably. I mean, I haven't taught axiomatic geometry in the East, but I have Chinese friends, very close Chinese friends, and we have many students from the East at St. John's, and I think what you see is that say with Euclidean geometry, it's got a certain, how to say, world historical power. Is that once you encounter it, you're changed. For example, the power of the axioms in the first 2 pages is that they assume that any human being with half a mind would be willing to go with this.
Yeah.
Right. That this makes sense. And so the beauty of Euclid is that, and the subtlety of Euclid is that he sees from the beginning what's going to make sense to a human mind. Right. And so he would bet that you go to anyone anywhere in the world, and you give them this page of axioms, and you start with book 1 to show how it works, and they'll be on board. So that by the end of book 1, they'll be on board. And so once you introduce that, everything changes. Right. And in someone like, so in China, the Jesuit missionary Matteo Ricci at the beginning of the 17th century went and translated the first book of Euclid's Elements into Chinese. Right. So it started then in India. All of Indian astronomy is derived from a book from the 1st century CE called the Pali Discourses, which is drawn from Ptolemy. Right. But then the Indians must have had the geometrical structure to understand that before. So I think there's a lot more exchange then than we think there was. But once it goes in, everything changes because it's so compelling.
So at one point there was a world in which no human being, likely no human being, had access to this axiomatic way of thinking. Maybe there were sort of flashes of it here and there, but sort of in terms of a systematized approach that students learned. This is perhaps bordering on the realm of a science fiction type question, but is there a potential for another way of thinking about the world that completely changes, again, how human beings interpret their natural surroundings, and that can make us look at the stars or each other in ways that we had never done before? I wonder, is it that these ancient mathematicians like Euclid and like the people before Euclid found these things which are equal to the same thing or equal to one another, right? There was something so clear, logical, and resonated with truth. Is that all there is, or because, or are there, or is there a potential? I'm sort of overwhelmed by this question here. Is human reason and cognition open to another moment, like the revolution of axiomatic mathematics on our thinking about the world and perception of the natural world and our place in it, and our meaning?
Surely there has to be, right? I think like 2,000 years from now, people are going to look back and say, "Oh, I can't believe they didn't see this." Just like in I think because of the success of Euclid's Elements, in a way that all our textbooks, all the ways that we try to communicate our conclusions are like Euclid's Elements. So we forget just how radical and original that book was. That there was nothing like it before. And once it came in, it changed everything. I'm sure that will happen again. But there's something, there's something that's very peculiar about Greek geometrical thinking, and maybe Greek philosophy. I hesitate. I don't usually use the word Greek because the Greeks disagreed about everything, right? And so, but in this case, I think there's something very interesting here. So in book 1, and especially those of you who've done it, you will understand this. So book 1 of Euclid spent a lot of time talking about triangles. and we do proofs about triangles. So we imagine triangles in our head, we draw triangles on the board, and then at a certain point we asked, well, what exactly are we drawing? Because a point, the three corners of the triangle, a point is that which has no part. So it's got no magnitude. It can't be divided. And a line is breadthless length. So it can't be seen. So technically, when you think about drawing a triangle, you're dealing with something that is not accessible to your senses, right? Now, then you go on with these proofs and you realize, well, I draw this triangle, I draw that triangle, I draw a long thin triangle, and I draw a big fat triangle. And what the proof is about is triangle. Not any of these particular triangles, but triangle, the general triangle. Right now, the general triangle can't be imagined. And so you think, well, Euclid was a Platonist, right? So Euclid thought that Plato characteristically thinks that the world around us, the physical world, can't really be understood because it's constantly changing. It's locked in a web of constantly changing relationships. But each thing that we see in it might draw from something that is unchanging. So I find I look around me and I might see triangles, I might see squares, but when I'm seeing those, so to use Platonic language, that each of those things that I'm experiencing participates in the idea of a triangle or the idea of a circle. And so one thing that this Euclidean geometry does is it wakes me up like your rooster to what Plato is talking about. Plato talks about it, Euclid does it. So you know that when you are doing these proofs of triangles, you're not proving anything about the triangle that you're drawing or even the triangle that you're imagining. You're proving something about a triangle that you see with your intellect, right? I say the Greek for intellect is nous, so I'd say a noetic entity, which for someone like Plato is more real than physical phenomena, because physical phenomena are always changing. They have no being. There's nothing that anything is. Whereas this triangle that I'm proving things about, it's got definite characteristics that don't change. And I can prove it in China, I can prove it in India, I can prove it in America, and I can prove it, in any century, the same thing holds true.
And it's fascinating to think, you take those things that will hold true always, that are more real than the world that we can touch and feel, but then put that back onto the world through astronomy, and in some way make that world more you. I mean, when you look at the sky, it's not it's more intelligible, having seen the geometric forms produced upon the motions of the stars, and you feel perhaps more connected to it insofar as it's more intelligible.
That's right. Yeah. So notice that your mind correlates with what's out there.
Mm-hmm. Yeah.
Right. Whereas the more modern dogma is that there's no correlation. One of the modern dogmas is that when you say something about the world, all you're doing is imposing something from your mind onto the world. And then I think for a Greek scientist, that you're discovering some kind of correspondence.
Yeah. Very interesting. Well, you've shared some of these figures with me over email, and I wonder if we could turn to some of these and look at some Euclidean figures and demonstrations. And which one would you like? Would you like me to pull up the first one you sent?
Yeah, pull up number 1.
Okay.
So, what I'm going to talk about is the Pythagorean Theorem, which nearly all of us had forced down our throats in in high school. And Euclid ends book one. The climax of book one is the Pythagorean Theorem. And I'll refresh your memory about what that is in a minute. But in order to get to the Pythagorean Theorem, which is number 47 in book one, so that the 46 proofs preceding that, which obviously I can't go through, but there are two important things that you need to remember before you get to the Pythagorean Theorem. And so the first one, and I haven't drawn it here, is to prove the equality of triangles by congruency, right? So congruency means that one of them fits on the other. So if you have two triangles, how do you know they're equal? Well, the simplest way to know they're equal is, do they have two sides and the angle between them equal? Right? So you have side, angle, side. And if you imagine like a couple of sticks with a fixed angle between them, if you have two of those sticks with a fixed angle between them, then if one side is equal to the side in the other triangle, if the other side is equal, the side and the angle is equal, then those two triangles are equal. So the way Euclid does it is that you take one side, you take one triangle, you put one side on the one side of the other triangle, and then because the angles are equal, the other side is going to fit perfectly on the second side of the triangle. And this means that if you connect the two lines, you have two triangles that are equal. So the most basic way of proving equality of triangles is that one of the triangles fits on top of the other triangle by side, angle, side. Now, this is this first idea of equality, which Euclid doesn't define, by the way. So with math, you're always proving things are equal, right? So equality is fundamental in math. And in geometry, the simplest form of equality is that one figure fits on another figure exactly. There's nothing less and there's nothing more. They fit exactly, and that is the proposition 1-4. You pick one triangle up, you put it on the other triangle, and they fit. Therefore, they're equal. Now, around proposition 40 in Euclid, things start changing. So in the top part of the diagram, you see parallel lines, and you see a blue-green figure, blue-green rectangle that sits on a base and has the height as the height of the two parallel lines. Now, if you take another figure with the same base, and I'm looking at the red parallelogram here, the red parallelogram has the same base and the same height as the blue one. So Euclid proves, and I don't have the time to prove it to you how he proves, but he proves that those two figures are equal. And you say, wow. If you go to the bottom figure, the one with the longer parallel lines, this emphasizes how implausible this is. So both those parallelograms, the little fat one on the right and the long extended one that goes across the page, those two are equal in area. And he proves that. And if you want to understand why that is, go read Euclid. You can put, but this is very interesting, because this is an idea of equality that is not based on congruency, right? In other words, you can't see that they're equal. This is arrived at through intellect, but you know that they're equal. And there's no way to prove that they're not equal, right? So even if this slanted, at the bottom of the page, this slanted parallelogram goes on for 5 miles, so it's very thin, so it looks almost like a line, they'll still be equal.
So yeah, so the reflection is that we start out with things that are intuitively equal, almost, yeah. Right? I mean, you drop one thing on you drop a triangle on top of another triangle, you line them up with prop forward, and there's something very intuitive, physical about that proof almost. But yes. From establishing that, we get to a sense of equality or we get to a demonstration of a quality that's not intuitive. That's very interesting. And I think, the history of math and science is a continual development of that sort of thing too. And now in modern physics, we're dealing with things that are, to some extent, incomprehensible in terms of its relationship to the world that we sort of touch and feel.
That's right.
But we get there ultimately from these building blocks.
Yes. So this removes us from our perception. Right, what we can perceive with our senses, but then what in my classes, one thing that always comes from this little proof is that hey, Euclid doesn't define equality, and around proposition 40 of book 1, we all start realizing that we don't know what equality is anymore. Right, so then it becomes a really interesting idea. Whereas in our society, we take for granted that we know what equality is, but if even in math, it's not straightforward, right? Let alone in politics or in morality, So all of a sudden, so one of the effects of studying something like this and being philosophical about it is that you start to get a certain distance from the basic concepts that you take for granted. Yeah.
And that's very powerful to see, I think, in mathematics, because I think we assume that concepts like equality are well defined and universally accepted by mathematicians, and that here, we're seeing that these are concepts that require some unpacking and some thinking about.
And maybe can't be defined. But one more thing before we move on to the next one. So in the middle diagram, the one with the triangle, Euclid's next step in proposition 41, which I believe those of you who study book 1 have studied, he then proves that if you have a triangle on the same base and under the same heights, that triangle will be half of the parallelogram. Well, again, so that's a relationship that is not given to your senses, but he shows that. So now I think we're ready for number 2.
Okay.
I'm hoping that these examples are fun, and that if they inspire people to study Greek geometry, it's going to give them one more entertaining thing to do in quarantine.
Yes, that would be really exciting if in quarantine everybody starts studying Greek geometry.
Yeah,
Amazon flying off the shelves, the elements.
Right. So
we're out of toilet paper in Euclid.
Yeah. You'll never be out of Euclid. So here is proposition 147, and this is Euclid's proof of the Pythagorean theorem. Now, if you remember, the Pythagorean theorem says that given a right-angled triangle, the square on the two sides around the right angle are equal to the square on the hypotenuse. So in this diagram, so you have right-angled triangle ABC. If you draw a square on side AB, the little red one, and if you draw another square on side AC, the two topmost squares, and then the squares on the side down the right angle at A, those two squares will be equal to the square on the hypotenuse, which is the side BC, which is the side in Euclid's terms subtend or opposite to the right angle. So BC is the side opposite to angle A. So in our terms, AB squared plus AC squared equals BC squared. So this is like one of the most fundamental theorems in geometry. And I remember having to memorize this in school and plugging in numbers. And I asked the teacher, why is this true, sir? I don't know, why is this true? And the only answer I got was, shut up, Venkatesh, just do it. And so it was only much later that I realized that he probably didn't know how to prove this. So this is how Euclid proves this. And we're going to see that there are actually many ways of proving this. And so part of the story of Euclid's Elements is why he chooses this way of proving it. And so let me prove it for you. So given right angle triangle ABC, I say that the square on the two sides around the right angle, the squares on the two sides around the right angle are equal in area to the square on the side BC subtending the right angle. So this is how Euclid starts with an enunciation. Given this and this and this, say that, right? And so how does he do this? How is he going to prove this? Okay, so he says, well, from A, the point of the right angle, draw a line AL, the green dotted line AL parallel to BD and CE, the two sides of the square. From F, the side, the corner of the smaller square, draw a straight line straight across to C. And from A, the top point of the triangle, draw a straight line down to D. Okay, so that's the construction. Okay, so Euclid always starts with the construction. So he has the enunciation, then he starts with the construction. And he never makes a proof about a figure that he can't construct. For example, you can imagine, maybe you can imagine, I don't think you can, an equilateral, equiangular, seven-sided figure. Euclid will not prove anything about this because he can't construct it. Therefore, it doesn't exist geometrically. But so we start with the construction. And so at this point, you stop in your reading of the proof and you look at the construction and you say, how is he going to prove this? Right? So now you look at those two triangles, FBC and ABD, those two triangles in green. And you'll notice that they're equal. You'll intuit that they're equal. Why do I know that they're equal? Well, because they have sides, side FB, the shorter side, equals the other shorter side, BA, because they're sides of the same square. Side BD, the middle length side, equals the side BC, because they are sides of the same square. Now, then you look at the angle at B. In the one triangle, FBC, the angle at B consists of one right angle, ABF, and one angle ABC, which is the, I guess, the fatter angle of the right angle ABC. Then if you look at angle ABD, you notice that consists of one right angle, CBD, and that same angle, ABC. So therefore, angle FBC and angle ABD are equal, right? So what you have there is that in those two triangles, they have side, angle, side equal, right? They have two sides and the angle that connects them equal. And so from the proofs of congruency, you know that triangle FBC equals triangle ABD. So this is equality by congruency. Those two are equal. If you pick one up, it will fit on the other one, right? So now what? And you say, well, okay. You say, very interesting. So why did Euclid draw that line AL? That's so AL. So then AL turns out to be the hero of the proof. AL saves the day. So with AL, you can see that there are two parallel lines, BD and AL. Right? So BD and AL are parallel lines, and on BD, if you think of BD as the base, you see a parallelogram BMLD. And then you see the triangle BDA, which is on the same base and between the same parallels as triangle BMLD. Right? So then this means, from proposition 41, that our little triangle ABD is half of the parallelogram BMLD. Right? So then you go to the red parallel lines, GC and FB. And we do the same thing there. So on FB, that's the base of a parallelogram ABFG, a little square there. And that on that base FB, there's a triangle FCB that is on the same base as the square and between the same parallels. Therefore, from proposition 41 again, that triangle FBC is half of the square FGAB, that little square. So what do we have? So we have the triangle ABD is half of the parallelogram BMLD, and the triangle FBC is half of the parallelogram FGAB. But those two triangles are equal. And if they're equal, then the figures that are double of them will also be equal. So therefore, the long parallelogram in the big square, BMLD, equals the square AGFB. Okay, so now he doesn't spell this out, but you just do the same with the other side. So if you do the same with the other side, then you'll realize that the corresponding side of this corresponding part of the big square, MCEL, the parallelogram MCEL, is going to be equal to the parallelogram AH, to the square AHKC, for the same reason as on the other side. So therefore, both of those little squares are equal to the square on the hypotenuse, which is what was to be proved. So there's your Pythagorean theorem done by Euclid. And it uses both equality by congruency and also equality using parallel lines.
You can see them together in this proof.
Yeah. And so one striking thing here is that you can't actually see that the squares are equal, that the two squares are equal to the third square. You can't see that, but we've proven it. We know it, right? Can we pull up number 3?
Yeah.
Thank you. So the top half of the page, and I don't think we'll have time to go to the bottom half of the page, but the top half of the page is very interesting because this proof is attributed to Pythagoras. So this is one Pythagoras used for the same theorem, and so Euclid must have known it. Okay, so what Pythagoras does is he gives you two boxes. He gives you equal boxes, and we're dealing with in the box on the left. You can see that we're dealing with a right-angled triangle. So you can see 4 right-angled triangles in there and 2 squares, right? And so one of those right-angled triangles is would be like the triangle ABC that we were proving about. So in the box on the left, you can see that a given right-angled triangle can be fitted in this way. You put 2 together to make a rectangle. You put another 2 together to make a rectangle. You join the corners, and then you have 2 squares on either side. You notice that the square on the top right corner is the square on the shorter side around the right angle. And the bottom left square, the bigger square, is the square around the other side around the right angle. Right? So this is box 1. Now, if you take the same size box and you now rearrange the triangles to get the figure on the right, right now you see that you can take those triangles and you can rearrange them to make this. And the square in the middle is the square on the hypotenuse. It's the bigger square that on the line that subtends the right angle. And so you have these 2 boxes, and each of these boxes is made up of 4 equal right-angled triangles, 4 equal right-angled triangles. And if you, in 4 equal right-angled triangles in one square equal 4 equal right angle triangles in the other square. And if you remove the 4 equal right angle triangles from both squares, you're left with the 2 squares on the left and the big square on the right. And this means, and since the square that holds them all, that contains them, is equal, this means that the 2 squares on the left are equal to the square on the right. And so this is Pythagoras' proof. So therefore, the 2 squares on the sides on the sides around the right angle are equal to the square on the side subtending the right angle. The square in A and the square in B equal the square on C. Right? So this is an interesting proof. It's very elegant. It's very beautiful. Mm-hmm. But it's like tangrams. Kind of you're moving figures around. You keep the same box and you just move the same figures around, and it draws on the common notion. You know, if equals are subtracted from equals, then what you get are equal. Mm-hmm. Now, I would say that this is very close to a visual proof, because all the equalities that you see, I mean, the equalities between the triangles are based on congruency, but then you infer that the squares on the left and the square on the right are equal. This doesn't require the proof of the proof using parallel lines, where you have this other kind of equality. Mm-hmm.
So
yeah, go ahead.
Yeah, so we're trying to show here that this square, the C square, is equal to the small a square and then the b square.
Correct.
Okay. And this proof sort of requires you to move the lines around in your mind and then infer, with very reasonable inference, though. I mean, it's not wrong.
Right. Yeah, right.
That the C square is equal to the A square and the B square.
Right.
Okay.
Yeah. It's it's not wrong. I mean, but this proof is not, it's not axiomatic. Right? You didn't need 2 pages of axioms and 46 previous proofs to get to this.
It's almost like it's almost like the proof in the Meno.
Yeah.
Right. I mean, insofar as that doesn't require Meno understanding the whole axiomatic system, with many propositions before that demonstration, and once some lines are moved around for him, he's able to understand the demonstration.
Yeah.
Or the servant in Meno, not Meno himself, but yeah. Right. This
kind of proof I call a fits in a box proof, but it also involves moving things around, which Euclid doesn't do. Mm-hmm. So I'd say that this would be an example of a way of doing geometry that is not Euclidean in style. So you'll see that geometers differ in style, but this is not Euclid's way. 2 things I want to say is that the first thing is that the significance of the Pythagorean theorem, and I don't know if you guys who studied book 1 talked about this, but there's a profound significance in this theorem that is also alluded to in the proof in the Meno. And the proof is, and the significance is this, is that the inner right angle triangle, the longer side, the hypotenuse, is incommensurable with the 2 other sides. Now what I mean is this. So incommensurable means there's no common unit, right? So if you think that, if you take say the length of your table, and then you say, I got a ruler, and if I take the ruler and I start it off at one end of the table, and I just keep turning the ruler over until it reaches the other end, if I extend the length of the table, sooner or later, the ruler and the table the ruler is going to measure the table exactly. In other words, the ruler will line up with the table, end of the table. So therefore, that ruler is commensurable with the length of the table, right? And so that means that they share a common unit. That means either the ruler is the unit, or there's some unit that measures the ruler is the unit of both. So you can say it's 1 inch. And one of the important things that the Pythagoreans discovered was that there's such a thing as incommensurability. Now, this is not, so it's possible to have two lengths, two magnitudes that are such that there is no common unit between them. Okay, you think about a square with side 1, right? So you have square side 1, and you draw the diagonal of the square, and you say, well, there's a square on 1 plus the square on 1 equals the square in the diagonal, and the square in diagonal is going to be 2. So the length of the side, the length of the diagonal is going to be the square root of 2. And it's not going to have the same unit as 1, because if you spell out the square root of 2 in decimals, it's going to go on forever, right? So it's not strictly speaking a number like 1 is. There's no common unit. And this discovery, it's not a practical discovery, because when we're practically measuring things, we always approximate, right? So we can say that this is more or less commensurable. That's good enough. But in mathematics, when you discover that that it's possible for magnitudes to be incommensurable, that means, wow, this is huge. I heard a story that the Pythagorean philosopher who discovered this on a ship he horrified his peers so much that they threw him overboard.
I heard that too, but also at St. John. So this might be a St. John's myth.
It could be a St. John's myth, yeah. But it's a good myth, because,
it is, yes.
Because I think it expresses the alarm that the early philosophers found, that hey, even with mathematical lines, with these seemingly simple mathematical figures, what if they're unintelligible? What if you can't express one line with another line? What if there's no universal principle of intelligibility? And so this proof is so important, because it says that even if the sides of the square, or the sides around the rectangle, the right angle in a right angle triangle, if they're not commensurable with the hypotenuse, then their squares are commensurable. And I can prove that their squares are commensurable. So they fit into each other. So therefore, I've got a principle of intelligibility. And so this is why this is it's so important. You start off with objects that are unintelligible to one another, and then you can discover through geometry some other principle of intelligibility that helps you to relate them. And so now we can play, right? So that's why this one is so important.
Interesting.
Yeah. But the other thing I wanted to say is that I was going to give you a lot of other proofs, but it would take another 2 hours. But Euclid, when he proves the Pythagorean theorem his way, he's trying to tell you a story. So he does it his way and not Pythagoras' way, because he's trying to include this more elusive principle of equality of figures within the same parallel lines. So he wants to draw that in, because I think he's thinking ahead. That he's thinking, if you understand how this works in this proof, you'll be kind of plugged in to some kind of mathematical principle that is not apparent to your senses, and that is that's more important for you to grasp in order to do some of the more complicated things that you'll do after. Right? So in the Euclid proof, that line AL really is the hero, and it will come up in subsequent proofs, because with AL you can bring in parallelism and everything that it implies. So he's telling a story.
Yeah. I want to pick up on something that you said at the beginning of the conversation here with regards to liberal education. I mean, in this way, you're just really describing Euclid as a fundamentally focused on liberal education, insofar as he's focused on freeing your mind, right? I mean, changing human beings' ways of understanding the nature of equality, perhaps also the nature of truth itself. Understanding the world through new eyes, showing us through a picture and a mathematical description a new avenue of human perception that's sort of fueled by a mathematical reflection. And that is, I think, just alone a good enough reason to study Euclid.
Yes.
in the context of a liberal education, in addition to the many other things that you've said about the importance of axiomatic mathematics in I guess the evolution of human thinking.
Yeah. And this stuff is fun.
It's really
fun
fun,
and it's beautiful, right?
Yeah. We in our book that we give to the students, we start out with Euclid with that poem. Euclid alone has looked on beauty bare. You know this poem, yeah.
Yes,
and we emphasize to them that this is a poem about the beauty of mathematics. Here we have the poet who is beside himself over over mathematics. And we hope to try to get students to a point where they can start to see the beauty in Euclidean geometry.
Yeah. People, mathematicians studied these figures for thousands of years before any use was found for them.
Yeah.
Right. So why would that be? It's because they're beautiful, and so and I think if you do that, you'll find that it's beautiful. You'll find that it's beautiful. It's absorbing, and as I say, if you sit there trying to figure out more ways of proving the Pythagorean theorem, it would give you dozens of hours of entertainment in social isolation. I guarantee that.
Well, maybe one of the good things that may come of social isolation these days is that people might be forced to find utility in useless things, and that utility might be understood as beauty.
Yes.